Okay, so let us get started. Uh, so, today we will see another kind of matching problem. It is like matching people to houses. Specifically, the motivating example comes from students' assignment to hostels. We know that whenever we come to college, join the college, we are assigned some room in a hostel which we do not like, and we like some others room, right, and we can't tell the authority, I think yeah, this recording I do not like. So, that sir, can you please exchange. Now, for authority that is a task, who wants to do job, I do not want to do extra work. So, for authority, no, this is some rule, institute rule, nothing can be changed, go away. So, what many students often do, which may not be completely under law and blah blah, is that I like your room, you like my room, let us exchange, or unofficially, right, and I do not know. So, many students, I saw many or many of my friends doing that during college time. I always abide by rules and regulations of wherever I am. So, I never do such malpractice, but I think I have seen many of my friends in college do that. I think that perfectly motivates this problem. So, the problem is there are n people assigned to n houses. That is one. So, initial allocation is given, and each person has a preference. Again, as I said, preference, there are many ways to model preference. Here we will assume again the simple ranking preference, which is ranking here. Over n houses. So, the question is, can you find a good allocation which is maybe better than this, makes more people happy, and satisfies other game theoretic properties like say strategy proof if possible. So, for example, if there are if I like your house, you like my house, and these are say hostel rooms, then we can exchange, and that is certainly Pareto better than the current allocation, right. Pareto better means that no one is unhappier and some guy are strictly happier. So, this is Pareto better. Can someone think of any other way to improve the current solution than mutual exchange? No. Yes, very good. So, what you can do, you can push this idea to cycles. So, this say I1 likes the room of I2, these are people, I2 likes the room to I3, IK, and IK likes the room to I1, and then we can do this exchange business along this cycle. That means what? I1 takes I2's room, I2 takes I3's room, and so on. IK takes I1's room. Everybody in this cycle are strictly happier than the earlier solution, and every people other than outside this cycle are not affected. they are as happy as before. So, it is Pareto better, and I think that this is sort of the main idea to get an algorithm which in some sense gives the best solution for this problem. So, let us see the algorithm and then let us then we will see in what sense it is the best what we can get. So, this let me explain the algorithm first. So, what you do is this, you draw a directed graph on the n people. So, I have n vertices, each vertex corresponds to a person. So, let us call 1, 2, 3, so on. So, these are the vertices and what are my edges? So, if I look at vertex I, so vertex I has exactly one outgoing edge and that edge points to that person's room which is most preferred. So, the edge, I have a directed edge from I to j if j's room is top preferred, best preferred by I, right. If there is a person, if he likes his room best, then have a self loop. So, self loops are fine. Out degree of every vertex is exactly once if you count self loop like that way, but of course, the in degree of a vertex can be more than 1, right. So, let us write the properties. Out degree of every vertex is exactly 1. Of course, in degree can be more than 1 or it could be 0 also, and we can have self loop. Now, we will implement this cycle business on this graph. So, first question is that can it be the case that this graph does not have any cycle? Yes. It can have a case. Can you give me an example of a case on say I do not know 2, 3, 4, 5? Self loops are cycles.
All of them points to a single person.
There will always be a
So, what is the right answer? But this is a requirement that out degree of every vertex is exactly once. You know, in the path graph, the end vertex, the out degree is 0, no?
You should have a cycle.
Should have a cycle.
Yeah.
Okay. Why? Can you give me a?
Using DAG and DAG structure.
Because if every vertex has an outgoing edge, so if we travel for n plus 1 times, then 1.
Yeah, I think that is a good enough argument for me. You can start from any vertex, say I, it has an outgoing edge, trace that path. Now, because it is I have only n vertices, there are only 2 ways to terminate. I traverse all vertices, but then last guy should also have an outgoing edge. So, in both cases I must have a outgoing edge which comes back to this cycle, to this path I am tracing, and this is the cycle then I am looking for, right. So, this graph always has a cycle. Counting self loops also, taking self loops also a cycle. always has a cycle.
So can we also argue like in similar way that if it would have been acyclic, then every DAG has a tail. So if this is not present here, so it would be cyclic. Can we say in that sense?
Yeah, but then you have to prove why every tag has a tail. I think this is a much cleaner, no? Then you have to prove why. Yeah. And why is in DAG? It is not directed acyclic graph.
No, like if it does not have a cycle, then it will be a DAG. Right?
Yeah. So
So we will show that every DAG needs a tail. So
okay, okay. Yeah, I think that's also fine. Yeah. So now the solution is staring at us once we have a cycle, because every vertex or every player points to the other player which is top preferred, that house is top preferred. If I do this exchange business along this cycle, then all the person in the cycle gets their best house, right, best possible scenario, dream scenario, and that is the algorithm. So, what is the algorithm? You get this graph and it has at least one cycle. Think self loops also a cycle. Once you got a cycle, this is an existential result. You can use any graph traversal DFS BFS to get any cycle, get a cycle, do this exchange business, and then what should we do then? Okay, then how about some other poor guys who are not part of any cycle? For the guys in the cycle, they are the happiest. They got the best house. They whatever they want, they got.
But there can be intersecting cycles also.
Yeah, very good. Can cycles intersect? No. Why?
Only one algorithm.
Sorry. Yeah, out degree is one again. So if the cycles intersect, I don't know. So if you have a cycle like this, maybe the edges are in this direction. Now, can there be a, so I don't know if so, because out degree of every vertex is 1, even if a cycle intersects at, two cycles intersect at one point, that is not possible then. This case is not possible. I think other cases also you can get rid of. I think this is also very important point. So, this is a very structured graph. So, cycles can't intersect.
For any intersection point, there will be two outgoing.
Exactly, this sort of thing. Yeah, correct. So,
Either here, like down or up.
no, these are tutorial things. So, prove that this is these cycles cannot intersect. You are not looking at my problem. I have to spend 1 hour and 15 minutes in tutorial. If I solve everything, what will I do in tutorial? Okay, so our problem is okay. So cycles can't intersect. Very good, thank you, good point. And so there are various cycles disjoint. I do my exchange along the cycles. The cycle people are very happy. But how about the other poor guys? How should we do, or what should we do? Any suggestion? Go for the second best house. Correct. So sort of that idea. A simpler way of saying that is all the people in the cycle, they got their best house, remove them from the system. Remove them from the system. Now I have a same problem, but smaller number of people, but the same problem. Repeat the same algorithm, right? So what's the algorithm? Very simple. I'll write. So you get this graph. There are cycles. At least once cycles are disjoint. For all the cycles, you do that exchange business and delete those from the graph. Now you are remaining with a problem with less number of people. Redraw this graph because you have deleted some vertices, and so you have a same house allocation problem, but less number of people, again do the same thing. Because here you see for example, if I exchange along this cycle, so these agents are gone, they are not part of system. So by redrawing, I mean again ask this guy, what is your best house, because these guys are not in the system. So then this guy may say, okay, my best house is maybe like now this. So you have to redraw this graph, which is not the same graph as deleting these cycles from this graph, right. For example, this edge will not be there, but a new edges will come. So let us write down that algorithm. Sorry. No, I am trying to get a good solution. So you came late, that is why. So the thing is, there are n poor students who joined and assigned sort of rooms which authorities seem best, look best, think it is best, and but they have different preference. So they are trying to doing exchange. So can we help them to get in some sense the best solution, which makes most number of people happy, and this in some sense. So what people often do is, I like your hostel room, you like my hostel room, let us exchange. So this exchange business I can do along cycles also, and again how, means what is sort of the best solution, that is the thing. You can say which maximizes total happiness, that sort of thing. So we will see what is the output and what good qualities, what good properties and desirable properties the output of this algorithm satisfy. Okay, that we will see. But this algorithm, is it clear to everyone? This algorithm, simple, very simple algorithm.
Why was priority given to the people in cycle to move first?
It is not about priority. So this actually the true answer to this, the output of this algorithm will have very good properties, and we will show, either I will show or you will show in the tutorial, that that is the unique solution with that good property.
So after deleting all these cycles, there will be set of distinct paths?
Yeah.
What you said that they will.
Sorry. So what is the question then?
My question is that, look, like if we delete all the cycles, so of course we will get set of forests in general graphs.
Correct. Yeah.
But here we will have only set of distinct paths actually.
Correct.
Like each path,
Yeah.
different paths we will have.
So that means once I get rid of the cycles, the other guys they can't hope to get the best solution, or may not get the best solution. May get actually, in the next iteration the cycle could be, this could form a cycle, then this guy is getting best solution, something like that. So we will see, yeah. So we will see what are the properties, but this algorithm, because it is so easy, and let me not formally write, this algorithm is called, you may have heard, top trading cycle. Cycle TTC algorithm. So it has both names. If you take algorithms, yeah.
So
Yeah.
after we remove the cycle, so say someone had the best room in the cycle, so that room is gone. So now this has no outgoing edge, so we will make an outgoing edge to its second.
Don't think like that. I think I think it's better to think much easier. You now have a reduced instance of the same problem. Those guys who got the thing, they do not exist in the input. That means what? That means those persons you delete, and from all the remaining persons preference, those rooms also you delete. So you have the same problem with less number of people.
Now then
Again draw the graph. Again you must have a cycle, these properties again hold, because the same problem, and continue till everyone is allocated house. Okay, so this is a TTC algorithm or TTCA, and the first observation is so let us prove this theorem. First of all, let me prove verbally because I will prove something stronger, that this is strategy proof. No agent can benefit by misreporting his or her preference. That is what strategy proof means. By the way, some guy, I think you raised a very important point that I forgot to stress, is that as I mentioned in my first lecture at the beginning, there are two kinds of game theory where utilities are either numbers, and here it is not numbers, it is just rankings, but the other things are same. Other you may have heard strategic form game or normal form games. So, here also you have all those things. In a normal form game, what do we have? Normal form game is a tuple n. Here also you have a set of players. I have a strategy set for every player in the normal form game. I had, right. So, here also each player has a strategy set. What is the strategy set? Preference, ranking. They have the choice of reporting their true ranking or any arbitrary ranking. So, you have a strategy set. We do not have utility functions. Utility functions you change with say preferences, say PII name. This is for without money. Here we had utility functions, right, and all standard game theoretic assumptions that this thing is common knowledge, rationality, intelligence, everything is there, and you can use all those or most of the game theoretic solution concepts like dominant strategy, weakly dominant strategy, equilibrium here also, because all are, if you look at say weakly dominant strategy, pure strategies, pure strategy Nash equilibrium, they are some equality constraint, some guy is happier here or happier there, which is encoded in these preferences, if it is ranking or something. So, all those concepts make sense. You can, I think you can, it is a good exercise to think. So, all those concepts make sense, all but few where there are probabilities. For example, MSNE does not make sense with these things, yeah, or mixed strategies does not make sense. Did we talk about mixed strategy, this sort of thing here? Okay. So, those things does not make sense with rankings, but all the pure strategies and all business with pure strategies absolutely make sense. Mixed strategies also make sense, but equilibrium concepts does not make sense. Yeah.
What is SI? That is preferences.
Exactly. Here the preferences.
Okay. So what is PI?
PI is the true preference. You can see. Very good question. So suppose I am a player. My PI is my true preference, that I really like that guy's house most, that is number one, that is number two, and SI is what I have to reveal, right, what I have to reveal. So, so here also we are doing same thing, strategy proofness. So, what by strategy proofness, what we mean here is that reporting PI is your best strategy. If your actual preference is PI, report PI to the system, and that is the best, that will yield you the best outcome. So, this is the same notion of strategy proofness works here also. Okay, so it is little digression, but let us come back here. Yeah.
It's not still clear to me that why you are not using utility function here.
Yeah, it's a long discussion. Can we take it over coffee? Yeah, but it's an important discussion. Or we can spend some time on this on the tutorial also, because that's an important discussion also. Let me do this. Yeah. Yeah, sorry. But if anyone is interested, please bring this question in today's tutorial. Yeah, it's very interesting thing. If everything is clear, why the entire machinery is developed there, why you are not using it, you are using something else, very important question. Okay, so the first observation is that this TTCA is strategy proof. Let us prove this verbally, and I will prove something stronger. So, why it is strategy proof? Can someone give me or tell me why it is strategy proof?
So according to the algorithm,
Mhm.
after the first iteration, we allot the rooms of the some people in the cycle with their first preference, and then as we move on, it will be like some players are allotted with their second preference and so on.
Yes,
And
but you
then
know, one important observation is that there could be a player who is allotted a room in maybe 10th iteration, but he is still getting first preference.
Some
Okay,
people,
yeah.
people might get second preference, and
Correct,
but
yeah.
others might get first or like.
Yes, yes, yes.
So it is strategy proof because if the person misreports
Mhm.
their preference, they might get allotted a room different than what they would have gotten
Correct.
originally, and it will be less than what they would have gotten.
Yeah, why less than?
Because in the first iteration we are removing the people who got their first
Correct,
preference
yeah.
and so on. Next it will be like first or second, first, second or third, and so on. So if they misreport, maybe the person, some people might get like their third preference.
Yeah,
Something
but
greater.
you know, it's not clear to me that if I am getting my fifth preference in 10th iteration, why by misreporting I may not, why I cannot get my say third preference in say 20th iteration. Yeah.
So, there are considered two distinct cycles here.
Mhm.
So they are being removed in the same iteration or in the
Same iteration.
same iteration.
Yeah. Yeah.
Like if my current top reference is part of a cycle, it might be allotted that, and due to misreporting, it will not be beneficial to me.
Correct.
In the cycle.
Correct.
If I'm not a part of the cycle, I could be near the intersection, like just pointing to a point which is part of the cycle, or I could be away from the cycle.
Mhm.
If I'm away from the cycle, when the cycle will be removed, I'll still be pointing to the misreported reference.
Okay.
And in the next iteration, I might be a part of the cycle and get the misreported allocation. And if I'm pointing to the intersection point, so the current reference which is misreported will not be allotted to me because it is part of the cycle.
Okay.
So in the next iteration, I'll go to the next possible reference, but the others, like the other players, will try to make a cycle and not include me. So
Yeah, sort of. I think the first part, yeah, clear. So let me tell. Yeah, it's not. It's a bit unconventional argument, but it's very neat when I saw. Divide the agents into these groups. N1 is the set of people allotted room say Ni is the set of people allotted room in the ith iteration. But before that, he raised an important question. So, let me clarify again. If the graph may have multiple cycles, they are disjoint. So, in the first iteration, I do exchange along all cycles. So, in the next iteration, so then again I do. Okay. So, it is not that in every iteration I pick only one cycle. Yes, yeah.
So can you argue that suppose it is strategy proof, I don't care about later while ranking set all.
just misreporting the first preference will not do me any good. Suppose if we prove this level,
Okay.
then which means the first iteration, they should not misreport their first preference.
Correct.
Then if we delete that, then again we apply the same level.
I think same kind of argument. Yeah, you are very close. Yeah, I think you have got the main crux of the matter. So here it may be more visible. So you define this set of people. N1 are the set of people who get their houses allotted in the first iteration, N2 and so on. So your set of people which is N is basically N1 union, these are disjoint, N2 say NT. If your algorithm made T iterations, this is the thing. Now, do you see that there is no incentive for N1 people in N1 to misreport, because they are getting their best house. So, there is no incentive for people in N1 to get their best to misreport. So, they will say report the true preference. Now, if they report their true preference, then these cycles, all these cycles which gave allocation to N1 exist, irrespective of what others do. Let me repeat, because people in N1 get their best house, they do not have any incentive to misreport. So, they report true preference. Now, if they report true preference, irrespective of what other people do, because those if some other people's preference change, then the edges outgoing from those vertices will change, right. So, the cycles, this is in the first graph, this was a collection of cycles. Now, if for these vertices the outgoing edges remain same, these cycles will remain same. Okay. So, for people other than N1 do not have any hope to get any house from N1, houses occupied by N1, right. Is that fine? Let me repeat, it does not matter what people in N2 to NT do or misreport, whatever they do, they cannot get hold of any house from N1. So, it is better forget N1 from this point of view. So, let us forget N1 in the proof also.
Then the game resets.
Then the game thinks. So, once if assuming N1 reports truthfully, which we can assume without loss of generality, then these houses are allotted among themselves, gone. These guys, then now look at N2. Now, people in N2, if they can't get any house in N1, if these houses are gone, they are getting the best possible house. So, assuming people in N1 are reporting truth, which is without loss of generality, the people in N2 also does not have any incentive to lie, because if they can't get hold of any house in N1, houses of N1 gone from the system, N2 are getting best thing. So, N2 also, people in N2 also does not have any incentive to lie, and so on.
So, sir, is it like greedy algorithm?
Sorry, algorithm is this. So, this is the proof that no people is better off by lying. Lying means misreporting her preference. Her true preference it is, yeah, this is a good thing. True preference is PI, but he has the liberty to report any other preference. So, this shows that it is not beneficial for him if he reports some other ranking other than PI.
So a person N1 can just report his best preference truthfully, but rest of the preference.
Think of the algorithm. So, algorithmically the input is whole ranking. So, this algorithm in your C code or C++ code, you are only looking at the top choice, and then constructing this graph, doing DFS, getting the cycles, removing this in the next iteration. These are part of algorithms. They are people. What algorithm you are saying?
But still, n1 can lie about other ranking from 2 to n, right?
But it won't matter because only one edge is
And it doesn't
from
matter, but I'm
each.
saying that is a different preference.
No. So okay. So strategy proofness means. So here is the important thing. So we are not unbiased. We are biased towards truth. We believe strongly that human beings are good, which is good. But so here is the what is the right term?
There is no
So let me tell you.
incentive
Yeah. So if strategy proof. So in game theory, we assume that if lying does not benefit, then any player will report truth. So what we have basically shown, if you know, this is strategy proof, but strategy proof there are various kind of thing. So this is what is called weakly dominant strategy. If you know, but if you does not know, that is better, not needed. So these are weakly dominant strategy. Truth telling is weakly dominant strategy. So it's like by weakly dominant strategy means that by misreporting you cannot get better, and there is a cousin or big brother called strongly dominant strategy, which says that by misreporting you will get worse. So whenever so strongly dominant strategy is such a strong concept, as the name itself suggests, that it is very rare in practical applications. So whenever we say strategy proof, we actually don't even ask for weakly dominant strategy. There is another notion called very weakly dominant. So that too we are happy with that. And what we basically proved is very weakly, which basically means that lying you cannot get better by lying. Okay. So more about this if you are interested in tutorial session. Okay. So here is a algorithm which is strategy proof. But coming up with strategy proof outcome is not difficult. Can you think of another another algorithm maybe, which is also strategy proof, different than this, different result? So that's why what we will show is more. It is even coalitional strategy proof. Yesterday I defined a notion called core. So in this algorithm, even a set of agent also cannot come together and change the allocation among themselves, so that which is Pareto better for them. So let me write. So the outcome of is the unique core solution. That is if so let me explain this. Explain the statement. It says that look at the output of TTCA, which is an allocation. It says that given that allocation, that is sort of the best. It makes everyone happy in the sense that there is no subset of players which can do again a mutual exchange of their hostel rooms and get a Pareto better solution, right? So obviously the initial solution, what initial allocation, what authority gives is not Pareto optimal. So in some sense, in this sense, this is the optimal algorithm, and here is also an important term. So such a solution is called a core solution. It basically means whenever you see core solution in any game theory related paper, depending on context, it basically means that given a solution, any subset of players cannot mutually exchange their part of the solution, their sub solution, which is Pareto better. That's without touching the other parts. So this concept makes sense in allocation. This is also an allocation task, but in other allocation problems also this notion of core makes sense. Whatever a group has been allotted a subset of people, they can't improve their happiness by exchanging their part, reallocating their group allocation. That's the idea. And here is another important term, unique. So it says that every house allocation instance has exactly one core solution. Solution is what? Solution is an allocation, allocating students to hostel rooms. That's the solution. And every such instance has a unique core solution. So how does non-core solution look like? A non-core solution is an allocation where there will be some subset of students who can do their exchange and get better off. Better off means nobody is worse off, at least one people is better off. That is called Pareto better. So in this sense, this algorithm is doing the best thing.
So your coalition is meaning they will exchange their rooms or they will lie?
No, not lie. Exchange their rooms. Exchange your allotted things. No, not lie. Yeah, important thing. So it's not a extension of strategy proofness. No, not that.
So exchange meaning what will they exchange?
So for example,
their initially allotted rooms. Or
no. So they are initially allotted a room.
yes.
TTCA took that allocation as input.
Yes.
Outputs another allocation.
Yes.
They take their rooms as per that allocation. In that allocation, no exchange business will improve.
TTC will give you the best possible.
In that sense, yeah, which makes sense. I think this is kind of thing what at least in students in my time look like.
But then we can also show that before TTC starts itself, if two people say together want to lie, then also they can't make anything better. Like here, we are seeing that only one person if lies can't make himself do better.
What I am saying, so are you talking about here strategy proofness or here?
The strategy proofness. We
In strategy proof, first of all, these two are different notions.
Yes, if one person lies, then he can't make himself better.
Correct.
That we show. Also,
That is strategy proofness.
if two people say lie together,
That we have not proved anything, sir.
like we
That
can
is
prove
called
that also.
coalitional strategy proofness.
Because core's definition was that coalition players can still not.
I think I made some mistake in the definition. So the notion of core is I think you are right. I did some mistake in the definition of core yesterday. It is not a extension of strategy proofness. It basically says that given for any subset of players, whatever resource has been allotted to that subset, they can't improve by exchanging, reallocating. This is, I have not written the definition also, because to write the formal definition I have to introduce many notions. But this is the thing which I will be able to prove also.
But the other thing that was like if two people lie together, still they can't be better off. That also
Correct.
we can prove.
Sorry, and
That
I
also
don't know.
we can prove it.
I don't know.
Like using this same argument that we use here.
Okay,
because
so-
N1 will always do the best. So in N2, if two people lie together, they will also not benefit. So like
No,
same.
I am very skeptical about proofs. if you think that's your thing, because I have to really verify. Many things from my childhood I have been saying. It looks I approve, and then people find mistake. I find mistake. So I will not accept to. Yeah. But let's come back here. So why I am saying strategy proofness is not a big deal. You have to show something stronger in this sense. Can you come up with another algorithm which is strategy proof? Authorities algorithm, nothing is possible. Input output same, so nothing is possible. So from algorithmic, if nothing is possible, what will you gain by lying, by misreporting? Input is same as output, output is same as input. So do whatever preference, lie, whatever you want, nothing is possible. So that's what I am saying. So you have to, in some sense, you have to show that your solution is a good solution, which is this is what this theorem encodes, and it is strategy proof. Yeah, in some way best solution and the unique best solution. Okay, so let's prove this. But yeah.
Let's say that there are two players.
Yeah.
Who want to exchange.
Correct.
That means that I likes J house and J likes I house.
My house, yeah.
But then it's forming a cycle.
Correct.
So then why is not a
better solution?
Yeah, in terms of exchange.
Yes, that gives a better solution. Correct. That's right. So this is the best in this sense. And if there is such a thing that I like your house most, you like my house most, this algorithm in the first iteration will do that exchange. Yeah.
Let's take a person outside, like we use the algorithm and then in the first iteration we have a cycle, right?
Correct, yeah.
Let's take a player outside that cycle.
Correct. So let's take this guy maybe.
Yeah. Say player A, and then player A misreports in such a way that he disturbs that cycle.
He can't disturb the cycle. It does not. So
like
this arrow will change.
Somewhere else, such
Okay.
that the
This cycle still remains. If he misreports, he has only control to his outgoing arrow basically.
Even if he attaches his outgoing arrow to any other in the cycle, still they
Yes.
have their first preference rate attached.
Even if it is here, this cycle is still there. Yeah. That is the crux of the matter. Okay, so let's prove this. Maybe I will show code and then you will show uniqueness in the tutorial. So the solution is here actually. Let's draw this again, just more pictorially. Okay, so it's again a proof by contradiction. So suppose not. Suppose the output of TTCA is not a core solution. That means what we have said, that that there exist a people who can change their allocation. That is very important. Their allocation, which is Pareto better. So let's assume there is a set S. Now let's draw this set S here. So suppose this set S. Let me write this Nj maybe. And suppose the highest this set S touches is Ni, and the lowest this set S touches is Nj. This is set S. Okay. Now can you give me the proof? It's just one line or two line. So I have just instead of writing like this, these sets I have just drawn it, because psychologists say with pictures students understand better. So I have drawn this picture, and now it is a proof by contradiction. I am proving core first. So, let us assume the output of TTCA is not a core solution, and then we will find a contradiction. So, if it is not a core solution, then by definition I have written A, let us write A. By the definition of core, if a solution is not a core solution, if there exists a set A who can exchange their allotted resource among themselves and become happier, Pareto better, yeah.
Nobody will collude with a class below them because that would give them a worse.
Very good. That's the crux of the matter. But I think many of you, for you, it's open also. Yeah.
So if you want just core and strategy proofness, I mean my belief is that this TTCA might be giving something much more. Because
Okay.
if you just want core and
Strategy proofness, yeah.
just make them stand in a line.
Yeah.
Ask them to pick their best in one.
That's what they are doing in the first iteration.
That's all is my algorithm.
But then how about others? That may not be a assignment. Each student. So here you see the first graph. No, it's not a big cycle. No.
There is no cycle. I just make all n students stand in a line.
Mm-hmm.
I ask the first student, ask them to pick your best house.
Correct.
And he will go with that house.
Okay.
I ask the second person, ask them to pick his from the remaining pool.
Oh, I see. I see. The standard thing. Whoever comes first. The standard administrative algorithm.
Yes.
That cannot be good because this is the unique core solution. So in that solution.
Okay. Any
Yeah.
permutation is score.
Uh,
Because nobody, I mean the same argument, nobody who came first in the line,
yes, I can see your thing.
but it is Pareto
Before
optimal.
assignment.
Sorry.
Before assigning anyone to room, that is what he's saying. Right?
I think I can't see bug in your argument, but it must have some problem, or it may be equivalent to this.
I think this gives, it maximizes the number of people who get their first choice. Subject to that, it maximizes number of people who get their second, some sort of.
No, but this is a unique core solution. That's my problem. So, if this theorem is correct, either your output is same as this output.
No, that doesn't give unique. It has.
No, yeah. But I can see your from where you are coming, and I can't directly refute that argument. Yeah. Okay, so let's come back here and let's prove code. So suppose it's a proof by contradiction, and suppose A is a subset who can exchange their houses among themselves and get a Pareto better solution. Now she has already given a proof. Any other one? Want to give a proof? Same, yeah. Yeah, it's and often this kind of things, this kind of proofs, it often helps with extreme things. So let's assume A is smallest such set. Right? If A is smallest such set, so because if there are many sets and they are finite, I can pick smallest. Now here look at Ni. Every person in Ni are getting their best house. So after this mysterious reshuffling that the players in A are doing among themselves, these people will still get the same house because they are getting the best house among this part, and they don't have any hope to get any house from here, right? So if among these houses, these people are already getting best house, and so they must continue to get that best house because it's a Pareto better solution. Then you can get rid of these people, and if A is a successful collision, that swap giving these guys same house, then you can reduce A. This is also valid because these guys are getting same house, but then how come this is the smallest A then? Okay, so just a minute. So often this pattern I have seen that whenever you are doing proof of this sort, where many examples exist, then assuming something extra on top of it, that okay, let's pick something which minimizes something, maximizes something, extra condition, puts extra structure which simplifies your proof. Without this assumption also it can be proved, but it just makes things much more simple. Yeah.
So just take two houses and two students.
Yeah.
And identical preference. They both like house 1 more than house 2.
They have an initial preference. That's important. Yeah. Oh, I see. Now I get your problem. So no. Now I have an answer to you. You're solving a different problem. The input to this problem, house allocation, is an initial assignment. It's not n person and n houses. So it's not that. They have an initial assignment given by authority, and the question is, now with this exchange business or whatever, can they be happier? Yeah, good. Now I find.
Different assignments will have different unique solutions.
Yes, different input is different. Think of like this: if an problem input is different, algorithm input is different, output will be different. Yeah.
Could you re-explain the difference between this problem and this?
So he is saying is that why not? So his thing is let's make all the students in line, what colleges do, and ask first guy, what is your best house? Give go. What second guy? What is your best house? Give go, and so on. This is a Pareto optimal solution. I think he gave the proof, but that's a different problem. For our problem, the input to the problem is an initial allocation, right? And the output is Pareto, correct? Yeah. With respect to that, yeah. With respect to initial solution.
So digressing a little bit. So in this case, we were doing first come first serve basis, right? So are there algorithms better?
No, too much digression. I have something more interesting to say also. So yeah, these are the different problems. That's the main thing. So here the question is, in the output also, everybody is at least as happy as the input solution. That is very important. In input, they also had a allocation. So their happiness can improve but cannot decrease. They are the authority of their thing. They can always tell the warden, these guys are doing this. Okay. Now, so this uniqueness part I am leaving, but the same idea will go through. Now let me introduce another very interesting matching problem, and you will appreciate it. So it is called kidney exchange problem, and it nothing special about kidney. This idea works for any organ, but given that we have more than one of that organ, and but we can live on one organ, so which is kidney. Every person has two kidneys, but it seems that one kidney is sufficient. So okay, so whenever some kidney failure happens, there are two kinds of treatments available in today's medical science. One is dialysis, that you go for dialysis, and another is if you can somehow convince someone to donate his or her kidney to you. Okay, and it turns out that if you get a kidney from some donor, your quality of life is much better than if you go for dialysis, and your life expectancy also increases, and that quality is also better. So in nutshell, kidney transplantation is much better solution, but the problem is you have to find your donor, right? And again, for legal issues, I think these are followed in US. I don't know in India whether there are laws or all. I am not aware of Indian laws, but in US and European countries, monetary transaction is not allowed for kidney donation. So you can't buy kidney. Okay, so you can convince maybe your parents or some close relative, wives, husbands, and if he or she can donate kidney, her kidney. Okay. So now okay, that's fine. So why are you talking in game theory thing? What's game theory? What game is going on? Now the problem is, suppose I have my kidneys have gone, it's not working, and or some persons, and that person's wife is willing to donate one of her kidneys, but because of say blood group mismatch or various other medical reasons, that kidney, the donor's kidney, may not be compatible with the patient. Okay, so here comes now the problem starts. So Let me explain, erase everything. So, this is called kidney exchange. So, here you have a patient 1, donor 1. So, you have various patients and their corresponding donors, maybe their relatives who are willing to donate his or her kidney to this patient, not somebody else. It is not the universal donor, not like that. P2, D2 and so on, PN, DN. Okay. And now here is one solution where the exchange comes into picture. If it happens that this donors is compatible with this patient and this donor is compatible with this patient, then this solves this their problem.
Here P2, D2 have relations, right?
If P1, P2 and D1 are compatible, let us draw an edge if they are compatible, and if P1 and D2 is compatible, if both edges exist, then do you see that they can say that let us exchange donors and then both the patients are beneficial. This is the idea of kidney exchange. Now let us model this in this is the idea of kidney exchange. Now what I and this can so this is pairwise exchange. And how many operations does it need? 4, right? 4 operations. Now again here at least European and US law says that even if someone gives it in writing that I will donate my kidney, before donation he has all the rights to pull away. So these 4 operations should be done in some sense simultaneously, because think of first donor D1 donates her kidney, his or her kidney to P2, and still P1 has not received the kidney yet, then D2 can say that I change my mind. You see the problem. So D1 has already donated P2, but D2 is yet to donate to P1, then this partner, this patient, corresponding patient, D2's patient got kidney. So the problem for this pair is gone. Then this guy may drop out, which is legally supported, even after writing on bond paper and those sort of thing in European and USA. So the point is all these 4 operations should be done simultaneously. Simultaneous donation. This in some sense restricts this sort of exchange you can do along cycles also. Let us see what do I mean by that. So suppose P1 is compatible with D2, P2 is compatible with D3 and P3 is compatible with D1, right. Here also you can do these 3 exchanges simultaneously. You can do kidney exchange along these 3 things, 3 people, 3 pairs. Is the diagram sort of clear? So again, but now 6 operations needs to be done simultaneously. Now because of physical bottleneck, there could be some physical cap on how many operations we can do simultaneously, which is really small number, because this is a big operation, small number. So what I am basically, so now from algorithmically, what is the problem? If I have suppose this sort of graph with these matchings and these sort of things. These ages encode compatibility, right. So, I am basically looking for, and I have a upper bound say L. L is the maximum length of a cycle. This comes from physical constraints, that how much infrastructure do we have, how many operations we can do parallelly, right. So, that is L, which is a small number, which is you should think of a 3, 4, 5 and so on. Then give me collection of cycles, each of length at most say L, right, which covers as many patients as possible. If I want to maximize the number of patients benefited, then my goal is to get a collection of cycles C1, C2, I do not care how many cycles, as many cycles as things, but they should be disjoint cycles. And disjoint cycles, and each of length of Ci is less than equal to L. Yeah.
Understand what do you mean by cycle? Irrespective of whether P1 and D1 are partners.
Oh yes, why am I saying cycle? Correct. What nonsense I am saying? Yes, correct. What cycles I am saying? Basically, these structures I am looking for. Now can you then how can I write down computationally? Means what is the computational task? Am I able to explain the physical thing, that these are the things, these are compatibilities, and at most L say operations can be done parallelly, maybe 2 L operations can be done parallelly, so that if 6 operations can be done parallelly, then along 3 things, 3 patient donor pairs can participate. So how does a solution look like? Number of edges
is constraint.
Number of edges is constraint, but any pair of edge, any set of edges is so for example, this could be 1, and then I do not know, say P3 and then P4 D4 P5 D5. So, solution is these are the input to the system, set of n patients, set of n donors, they are corresponding donors, not they are and they will donate only if their patient gets their kidney, which makes sense I think in practice. And give me a solution, we have to figure out what does solution look like, because it is not just any matching, right. Because any matching, it basically says that whenever you have to find a matching so that it looks clumsy, you have to, if you match a patient, you should match its donor also, right, and in some sense they should this cycle which looks intuitively should be of length L, means your solution should not ask to perform more than 2 L operations simultaneously.
So we want to reduce them to bipartitions of L size, at max L sizes, different bipartitions.
Yeah.
So partition this problem into different bipartitions of max L size.
No, so I am still we are still thinking of what is the right formulation. No, we are theory people, we want a clean solution. Okay, graph, tell me what to compute, then I will compute algorithm, approximation, FPT, all those things we will do, but here it is not clear.
So if we connect an edge to P1 D1 P2 D2, then we can just say that we have to find disjoint cycles, then it won't be complicated to
It's like a permutation, right? But in cycle it's like a permutation.
If I connect this, then it is just disjoint cycles, is it?
Yeah, for every of maximum length 2L at
Yeah, say L is some parameter. Yeah.
We can also say that
I think we can even get rid of the patients completely, because donor DI will never go to surgery without patient PI going to surgery.
Yes.
So we can just keep DI as representative of both PI and DI,
Yeah.
and just deal with that graph.
Good. Actually, so who proposed this thing? Yeah. So I do not immediately see the problem with this approach, this formulation also, let me think, but that his formulation is what community has taken, and then let me present that formulation. So, what we do here, we have n patient donor pairs till here Pn, and for every pair I have a vertex 1, 2, 3 and so on. I have a edge from I to j if the donor of I can donate kidney to the patient of j. Okay. So, this is like kidney is going. So, I can have this also possible if the donor of j can donate kidney to patient of I and so on. So, in this directed graph I am looking for disjoint cycles, maximum disjoint cycles each of length at most L, covering as many vertices as possible, because each vertex as a patient. Okay. So, find collection of cycles, disjoint cycles each of length at most L, covering a maximum number of vertices. So, this is the underlying computational task in this kidney exchange, and if L equal to 2, then which problem this is basically?
L is number of surgeries or length of cycle?
Say length of cycle, because they are constantly related.
Okay.
Yeah.
L is, that is
If L equal to 2,
matching.
then do you see it is a matching. What I do is that whenever between any pair of vertices both these edges exist, I put an edge, undirected edge, and other edges I delete. So, because these are the only possibilities if L equal to 2 length cycle. So, for L equal to 2 this is polynomial time solvable. For L equal to 3 onwards, for every constant L, this is NP complete. So, okay. And then we have from algorithmic side we have some algorithms. There is a big O star of 2 to the power n time algorithm. This is on exact algorithm on with classical complexity, not parameterized, and we have lots of FPT algorithms also. Okay, so this is sort of one kind of, again you see all are matching problems at the heart. This stable matching, this house allocation, and this is also matching problem in some sense. But each application brings its unique sort of constraints, and the underlying game theory tells us what kind of solutions we are looking for, and have different algorithms. And these are only few examples I have just picked. So, there are various other kinds of problems whose background or motivation comes from game theory, and then at the end we get a computational question, and we look at algorithmic aspects, complexity aspects, parameterized complexity, algorithms, and so on. So, this is a broad area of research in algorithmic game theory. Okay. So, in the next section we will stop matching because and move or introduce another very interesting line of work on voting theory. Okay, but just I am re-emphasizing that it is just a tip of iceberg. There are many variants of other problems, matchings and so on, fair division, dividing, resource allocation. I think that is a thing. There are various variants of resource allocation which has been studied from game theoretic point of view, and once you study from game theoretic point of view, then algorithmic questions also make sense, and it is a huge line of research. Okay, so let us stop here.